Alright, so we can restart from where we left last time. Can anyone please remind me what we talked about last time? Okay, so far last time we looked at using the concept of energy to find the equation of motion of a certain system. Instead of using the concept of force, which is what we were doing before we were looking at the equilibrium of forces or equilibrium of moments in order to determine the equation of motion. Again, in this case, we are using the concept of energy. We went through a couple of simple introductory problems, and we started by looking at this example here, where we have a mass that is suspended with a spring. So what we do, we just need to look at the principle of conservation of energy, which of course can be used when we have a conservative system, which means basically we have no friction, no heat loss. And if this is the case, we are in a situation in which the summation of potential and kinetic energy is constant. So what we need to do, we need to simply look at the kinetic energy of the system, the potential energy of the system, we put them together. In this case, the kinetic energy is related to the velocity, the potential energy is related to both the gravitational force and the force of the spring, so we can include both contributions, and then we take these three terms, we plug in this equation where we have v and v plus t equal to constant. We can simply derive this expression, we derive with respect to time is our variable here. So once we derive with respect to time, here we have constant, the derivative is 0. In this case we consider also the static equilibrium when the weight balances the force of the spring, and then we can write the final expression of the equation of motion, which is of course identical to the expression of the equation of motion that we found when we were using forces. Another very simple example is the pendulum. So exact same concept, summation of kinetic and potential energy constant. In this case we have rotation instead of translation, which means that the kinetic energy is expressed in this way, 1 over 2I omega square. So instead of the mass we have the moment of inertia, instead of the linear velocity we have the angular velocity. We can find the expression of the inertia, of the moment of inertia, and then regarding the potential energy, in this case we have only gravitational potential energy, so basically we need to find the h, so the height of the mass at a certain time. So we have the difference between the entire length and this term here, L cosine theta, which is basically this term here, and same thing, we can plug all this expression of kinetic energy and potential energy in the expression t plus v equal to constant. We can derive, we simplify. In this case we can do a further simplification because we said, okay, let's consider only small displacements. For small displacement the sine of theta is equal to theta, so we can again make this simplification, we obtain this equation, which is of course identical to the equation that we obtained when we were using forces. Make sense? Alright, so when we looked at another problem that was a little bit more involved in this case, because here we have a mass, here we have a disk, the mass is connected to a linear spring, the disc is connected to a shaft which has its own torsional stiffness. So when we look at this, same thing, we look at the total kinetic energy, we look at the potential, also total potential energy, we plug these two quantities in our t plus v equal to constant. Of course in this case we have to be careful, because even if we have two types of motion, we still have 1 degree of freedom, because we assume that there is no slip condition between the mass and the disk. So the rotation of the disk and the translation of the mass are related to each other, they are not independent, which means again we have only one degree of freedom. So we can relate these two quantities. When we relate these two quantities, we can plug the expression of theta as a function of x here, so we have everything as a function of x. Once we have this expression, we can derive the expression and we can simplify, and then we can group together the terms in x double dot and the terms in x. We can write everything like in the standard form, and then from the standard form of the equation we can quickly find the natural frequency. Make sense? Any question about this concept? Alright, if there are no questions, we can take a little step forward. Today is 2. Alright, I would like to talk a little bit more about using the energy method, because what we saw before is related to using the energy method to find the equation of motion. But we can also think a little bit further, and we can use the energy method to directly find the frequency, the natural frequency of the system. This is valid, and we can do this by looking at simple example. So let's assume that we have a system like this, where we have a mass that is connected to the wall with a certain spring. So we have K, and our motion is in the horizontal direction. So we can start still from the principle of conservation of energy, so which means that we have the summation of potential and kinetic energy is constant, so T plus U is equal to constant. Of course, we can expand this, and if the summation of potential and kinetic energy is constant, it means that at two different instants in time we will have a certain amount of kinetic energy and a certain amount of potential energy. Now, the summation between these two must be equal to the summation of these two quantities at another time, because T plus U is equal to constant. So we can rewrite this one as T at T1 plus U at T1 must be equal to T uppercase T at T2 plus U at T2. So this is basically an expansion of this expression here. We can simplify our notation. We can simply write T1 plus U1 equal to T2 plus U2, where T1 is kinetic energy at instant 1, U1 kinetic potential energy at instant 1, and so on. We can rearrange this expression, and then we can see that we obtain that the difference U1 minus U2 is equal to T2 minus T1. Right, I simply rearrange this in order to obtain this. So basically the difference between the potential energies at two different times is equal to the difference between the kinetic energies at those two times. Which means also that when we look at this expression here, we may have a situation in which during the entire cycle of the motion we may have either zero potential energy or zero kinetic energy. And this is something that occurs when we look at the pendulum, when we look at the simple harmonic oscillator. So in this case, it means that we can also write the following expression, that when we have zero, at some point zero potential energy, we will have in some other instant maximum potential energy, and same thing occurs for the kinetic energy. If we have at some point zero kinetic energy, we will have at another point maximum kinetic energy. So basically we can rewrite this one as U max equal to T max, because again at some point we will have zero potential energy, and at some other point we can have zero kinetic energy. So the maximum of the potential energy must be equal to the maximum of the kinetic energy. Now, if you recall the expressions that we used for the displacement and velocity as a function of time, at some point also we talked about the maximum displacement that you can have, and also we talked about the maximum velocity that we can have. And we know that potential energy and kinetic energy are related to displacement and velocity. So in this case, when we have the spring, if we look at the potential energy, we know that it is related to the spring displacement. And we also know that the maximum displacement would be simply the amplitude of the displacement function. Because remember that the displacement function x of t equal to a sine of omega t plus phi has the maximum when the sine function is equal to 1, so the maximum displacement will be simply the amplitude. Right? So from the maximum displacement we can also find the maximum potential energy, so we have that U max is equal to 1 over 2 Ka squared. We can do the same with the kinetic energy. We know that the kinetic energy T is related to the velocity of the mass. We also found previously the expression of the maximum velocity. And if you recall, that was given by A omega n, which means that the maximum kinetic energy is equal to 1 over 2 m, so the mass of the body, multiplied by this expression here, which is A omega n squared. So we found the maximum potential energy, 1 over 2 Ka squared. We found the maximum kinetic energy, 1 over 2 m A omega n squared. We can plug these two quantities here and we obtain 1 over 2 Ka squared equal to 1 over 2 m A omega n squared. When we put these two together, we can simplify, because we can get rid of 1 over 2 and 1 over 2. We can get rid of a squared and a squared. So when we remove all this, what we obtain is k equal to m omega n squared, which means that from this one we can obtain that omega n is equal to the square root of k over m. Which is exactly what we were expecting, because before, when we were looking at the natural frequency, this is what we found for, remember, undamped single degree of freedom system. Make sense? Yeah, well, yes, the kinetic energy is related to the velocity of the mass, right? So the maximum velocity of the mass, if you recall from a few lectures ago, is a omega n, so we can find the maximum kinetic energy as 1 over 2 m v squared velocity squared, which is a omega n squared. and then again we plug these two expressions here and here, and then we can simplify, and then we obtain the exact same expression of the natural frequency. Make sense? Any question about this? So if there are no questions, we can look at an example. So we can look at a system that looks like this. So you have a certain mass m, which is attached, so this is a disk of mass m, this is attached to the wall through this spring K here, and what we have to do in this case, we have to find the natural frequency. So I want to give you a few minutes to look at this problem. Yes, in this case we can assume no sleep Yes, that was muted. Yes, we can assume no sleep condition in this case, yes. 5 seconds and everybody should be back. Alright, everybody's back. So I need to open. Alright, how do we approach this problem? Yeah, in this case we also need to consider, in comparison to what we saw right before, we have to consider also the rotational kinetic energy, because here we have that this disk is translating because it moves back and forth, but it's also rotating around its own center. So when we look at the energy, kinetic energy, we have to consider the two contributions of rotational kinetic energy and translational kinetic energy. So we can start by looking at this. So the total kinetic energy is, as we just said, the rotational kinetic energy and translational. Because in the problem that we saw last time, we also had one contribution of kinetic energy and one contribution of, in the problem that we saw last time, we had one contribution of rotational kinetic energy and one contribution of translational kinetic energy. But in that case, they were coming from two different bodies. One was the disk that was rotating around its own axis, and the other one was the mass that was going back and forth on the horizontal plane. In this case, the two contributions of rotational and translational kinetic energy, they come from the same body. Because again, this little wheel here is both rotating and translating. Makes sense? Now, the way how we write down the rotational and translational energy will be similar, the same of what we saw last time, but again, in this case, they come from the same body. So for the rotational energy, we have 1 over 2 j theta dot squared, which is the rotational which is the angular velocity, and then we have 1 over 2 m x dot squared. Even in this case, even if we are actually looking at two variables, the two variables are related to each other because of the no-slip condition. So a certain amount of rotation corresponds to a certain amount of translation for the body. So we can write x equal to r times theta, which also means that x dot is equal to r theta dot. Since we want to write everything in terms of x, we have to express theta as a function of x, so we have that theta dot is equal to x dot over r. We can now take this one and we plug here, so T, the total kinetic energy, will be equal to 1 over 2 j x dot squared over r squared plus 1 over 2 m x dot squared. Remember, we have to look at the maximum value of the kinetic energy, and also we will see at the maximum value of the potential energy, which means that x dot max is equal to omega n times a. We put this in a box because we are recalling this expression. So the maximum kinetic energy will be equal to 1 over 2 j, and then here we replace this one, so we have omega n squared a squared divided by r squared, and then plus 1 over 2 multiplied by the mass, and then the same thing, omega n squared a squared. We can group things together, so what we obtain is 1 over 2 j over r squared plus the mass multiplied by omega n squared and then a also squared. So 1 over 2 is on both sides, omega n squared times a squared is also on both sides, so we are left with j over r squared plus m. And this is the maximum kinetic energy in the system. On the other hand, when we look at the potential energy, this is a little bit more straightforward because it is identical to what we saw before. So we have that U max, so the maximum potential energy is 1 over 2 k x max squared. We know that the maximum position is basically the amplitude of the response, so we have 1 over 2 k a squared. We can now put these two together, actually these two together, because we have that T max must be equal to U max. So we have 1 over 2 j over r squared plus m omega n squared a squared equal to 1 over 2 k a squared. We can simplify. 1 over 2 is on both sides, a squared is on both sides, so we have j over r squared plus m. This multiplies omega n squared equal to k. Since we want to find the natural frequency, we have that omega n is simply the square root of k divided by this quantity here, j over r squared plus m. And this is what we wanted to obtain, the natural frequency. Yeah, so basically what you did is to do the same things that we were doing when we were looking at using the energy method to find the equation of motion. So of course if you use the method to find the equation of motion, and then from the equation of motion you can obtain the natural frequency, or you can go in this way and then you can obtain directly the natural frequency. Of course both methods must bring you to the exact same solution, the exact same result, unless there is something wrong in either the step of one way or the steps of the other way. But basically what you did is to do the summation of kinetic and potential energy, you equal this to a constant, and then you derive, it becomes zero, you obtain the equation of motion. So the same steps that we were following before, of course, will bring you to the exact same result. This is again a little bit more straightforward to go directly to the natural frequency, but of course both ways are acceptable if it is not specified and if you are asked to determine the natural frequency. Make sense? Okay, good. Any question about this?